Hey guys, I just want to say a little bit more about this magic number of the dimension of a vector space. Knowing the dimensions of vector spaces is a really important thing to the theory of linear algebra in general, and it's going to play an important role for us for the rest of this course. So remember that the dimension is just the number of vectors in any basis for V. Right? There's a correct number of vectors that you have to have in a basis for any vector space. Okay? And you might wonder, let's suppose that the dimension of V, let's suppose that it's n. And let's suppose that we have a set S that has k vectors in it. Right? So you might be wondering, well, what goes wrong if k doesn't equal n? Right? Well, I'm just going to give you a quick little summary of what goes wrong right now. And the summary is just this. If I give you more vectors than whatever the correct dimension of your space is, so let's imagine that I gave you like 4 vectors in R3. Okay? Then what I claim is that that set S cannot be Li. I mean, if you take 4 vectors in R3, let's just make up some vectors here. I don't even care what they are. Right? That's 4 vectors in R3. I claim that I don't care what the numbers are that you made those vectors out of. You have to have a free variable. You must have a free variable here. Do you see that? Because after all, you can only have 1 pivot per row. And I only have 3 rows, but yet I have 4 columns. So there's going to be a column here somewhere that does not have a pivot. And that means there's a free variable, and that means S is not going to be linearly independent. Okay? Now, S might span the space. That is still a possibility. It might span V, but even that is not guaranteed. Imagine that I gave you, you might feel like if you spend a lot of money buying a lot of vectors, right? If K is a big number here, you have a lot of vectors in your hands, you might think, well, surely they would span the space at least. Well, not necessarily. What if these are the vectors that I gave you? Right? I gave you, you spent $6,000. You spent $6,000 buying the vector 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, and 6, 6, 6, right? Spent a lot of money on that, but guess what, guys? When you do the EROs, this is going to cross off, and you're going to get a pivot over in the far right column. You are not guaranteed that S spans V, even if you have a large number of vectors. And you already know that S is not Li. Okay? On the other hand, what if K is smaller than N? Well, in this case, S cannot span V. This would be the case of, let's say, a tall skinny matrix, right? So if I had something like this, 1, 0, 3, 4, 2, 1, 1, 1 or something, right? And suppose we were trying to span our space here, right? Well, you know that you're going to get this third row, for example, is going to get zeroed out by the elementary row operations, and you're going to end up with a pivot over here in this far, far right column, and that's bad, right? For a tall, skinny matrix like that, there's no way that S could span V. And S might be Li. Okay? No guarantees. Right? There's no way to get a fast yes out of this one. Okay? If you have too many vectors, the set won't be Li. If you don't have enough vectors, they won't be able to span V. That's what we can say for sure. All right? But as to whether we can say whether the opposite property is true or not, we would have to do more work. We would have to actually row reduce the matrix and follow the pivots and the free variables to see whether we have a spanning set or a linearly independent set in those two cases. Finally, if k equals n, what if I give you exactly the right number of vectors? Are they guaranteed to be a basis? No, they're not. They're not. In fact, we can form that square matrix, right? And if k is equal to n, we're going to get a nice square matrix. It's not going to be tall and skinny. It's not going to be wide and fat. It's going to be exactly a square matrix. And I'm just going to say that S is either both. It is a spanning set and linearly independent, or it's neither. It's one of these two choices. And it just hinges on whether the determinant of that matrix that we've been building is 0 or not. Remember, a non-zero determinant is a good thing, right? That's going to mean that S is both a spanning set and linearly independent. In other words, it's a basis. But if it's not a basis, if I gave you the correct number of vectors and it's not a basis, I can promise you that it's actually going to be neither a spanning set nor linearly independent. Both conditions are going to fail. So just playing this counting game, see, I got 3 cases here, right? Just playing this counting game, we can answer a lot of questions really quickly. So here's an example. Is the set of 117 minus 89x, comma, 51 plus 261x squared a basis for P2 of R for the polynomials of degree 2 or less? Well, I claim this is easy to answer because we know that the dimension of P2 of R is 3, but we were only given 2 vectors. K is 2, right? K is the number of vectors that I'm giving you. In fact, K is less than n. N is always what I'm referring to as the dimension of whatever my vector space is. So I have actually this case right here. 2 is less than 3. Those vectors cannot possibly span P2 of R. It turns out that these 2 vectors are linearly independent. So this set is Li only. It is not a spanning set. It does not span P2 of R. Do you know why the vectors are linearly independent? I can actually say that without even doing anything in this case because I only have 2 vectors here. Let me remind you that when you have exactly 2 vectors, right, those vectors will be linearly independent exactly if and only if those vectors are not scalar multiples of each other. These 2 polynomials are not scalar multiples of each other. So it is a very safe bet that they are in fact linearly independent. You can get away with that when you only have 2 vectors in your set. You can't get away with that if you have more than 2 vectors in your set. Okay. Yeah, so if I give you the wrong number of vectors and I ask you, is it a basis? That's an easy question, right? If I give you too many vectors, it's not a basis because the vectors can't be Li. If I don't give you enough vectors, well, then they can't be a basis because they aren't going to span the vector space. This is why it is so important to know the dimensions of the vector spaces that you typically are working with. So, you know, let's just maybe just throw one more example up here, right? So suppose I gave you, let's take V to be the set of 3 by 3 skew symmetric matrices. Okay, and then let's take S to be, I'm going to make a list here of some 3 by 3 skew symmetric matrices. Let me just do this. There's one. Let me make up another one. Something like this. Okay, let me make another one. Something like this. And I'll make another one. Okay, so there is a set of skew-symmetric matrices. You'll notice the form right off the bat. I have, pretty obvious that I have k equals to 4 here. I have written down 4 skew-symmetric matrices. What is the dimension of V? We need to know this because this is what I've been calling n. N is the dimension of V. Well, we've actually looked at skew-symmetric matrices before. Remember that the form of a 3 by 3 skew-symmetric matrix is always of this form right here. Okay? Does that help you figure out the dimension of V? If this is the generic form, and I wanted to span all of these matrices, what would I have to do? I would have to bust out the variables, right? I would take out the A, right? The A would be multiplied by this matrix, right? And I bust out the B, we've seen this before, and so on, right? We bust out the C, we get one more example here. And these 3 matrices, turns out, is both a spanning set and linearly independent inside of V. My dimension is 3. I have 3 vectors here. 3 vectors in the basis. So this is my basis for V. I have 3 vectors there, so n is 3. So are these matrices going to be a basis? These numbers don't match, right? K is bigger than n. It's too many vectors. S must be LD. It must be LD. It's not a basis because to be a basis, the set would have to be Li and a spanning set. Now, this set of matrices might be a spanning set. That would take further investigation. We would have to actually take these matrices, lay them into the columns of a rather humongous matrix, do row operations on it, and see whether a pivot would drift into the far right column. I'm not going to do that right now and here, but that would be the idea behind that. So, these vectors are LD. There has to be a linear dependency. And by the way, to find the linear dependency among these matrices, we would also have to do a fair bit more work, right? We're not going to do that right here. We're just going to say, look, we can count 4 is bigger than 3, so the vectors have to be linearly dependent. Okay? I hope this idea of basis and dimension is making some sense. Again, the dimension of a vector space is just the number of vectors in a basis. And you have to have exactly that right number. It's a magic number. If your set that's given to you is too big or too small, it won't work, right? These are just a couple of examples. Keep playing with it. Ask me more questions. We can do more examples. But I hope you've been enjoying some of this theory of linear algebra. It is very important stuff. Thanks, guys, for watching. I'll see you all again real soon.